Hey everyone, our research topic is analyzing automated breast ultrasound images using deep learning and convolutional neural networks to detect breast cancer. Today, Gautam, Tanasia, Bhavya,
I don't see your presentation.
Neil, and I will be presenting for you today.
So the problem being addressed is that current cancer detection models analyze X-ray images, CT scans, MRIs, and other imaging processes which use radiation or other dangerous wavelengths which can cause cancer. So the chance of getting a fatal cancer from any one CT scan, for example, is about 1 in 2,000. And another downside of the imaging processes used in current cancer detection models are that they're expensive. So on average in the US, X-rays cost up to $500, CT scans cost up to $3,280, and MRIs cost up to $12,000. So ultrasounds are the perfect imaging processes, is a perfect imaging process in terms of expense and safety. So on average in the US, ultrasounds cost up to only $800, and ultrasounds have no radiation. So the problem is that despite the inexpensive and safe characteristics of ultrasounds, they lack the sufficient detail to detect small masses of cancer compared to the other methods of imaging. So the question we're trying to answer is, can we find a way to detect these small masses of cancer growth? Can we find a way to detect these small masses of cancer growth in ultrasound images to make cancer detection more affordable and safe?
Thanks, Gautam. So now on to prior research. First, we have the Liu et al. Model. So Liu et al. Developed an innovative approach for breast cancer detection and classification using a 2D breast ultrasound known as bus images. Their model employs a grid-based deep feature generator to improve accuracy while reducing the computational complexity. So here's how it works. The bus image is first divided into 8 different grids. Then 16 pre-trained CNN or convolutional neural networks architectures are applied to extract features from both the full image and the grid sections. Through evaluation, the 3 best performing CNNs are selected. In this case, ResNet 101, MobileNet V2, and EfficientNet V0. The model then uses INCA, or Iterative Neighborhood Component Analysis, to select the most informative features from the combined output of these CNNs. Finally, a deep neural network, known as a DNN, classifies these features to determine whether the breast tissue is normal, benign, or malignant. This approach achieves a high classification accuracy of 97.18% for these 3 classes. The grid-based feature extraction and selective use of pre-trained models help to minimize computational overload while maintaining high performance. The framework is also designed to be extendable, allowing for the incorporation of additional pre-trained networks as they become available. The model's ability to automatically select the most appropriate CNN architectures for the task at hand make it adaptable to different datasets and imaging conditions. This innovative approach shows promise for clinical applications, potentially assisting radiologists in early detection and accurate diagnosis of breast cancer. All right, the next model was created by Ahmed et al. It also detects breast cancer. Ahmed et al. Proposed efficient neural architecture search to detect breast cancer in ultrasound images. ENAS is a reinforcement learning model that creates 2 optimal cells, a normal cell and a reduction cell. The 2 optimized cells are shown here. They then manually put together a CNN architecture using the generated cells, and they created 2 models, ENAS7 and ENAS17, which proved to be more accurate than the AlexNet and CNN3 architectures.
The Sybil model was created by a group at MIT to detect lung cancer in low-dosage CT scans using previous research in various CNNs, reinforcement learning, and a different feature selection algorithm to create a model to accurately detect cancer. They used the ResNet CNN architecture to extract features from each image and then input them into a max pooling layer, which is used to reduce dimensions of each feature vector but keep the most significant features. The final feature vector is sent through a hazard layer to predict the risk of getting cancer within the next 6 years. In their testing period, Sybil was able to predict which lung would eventually develop cancer, even though there was no visible evidence of any developing cancer in the image. It was tested across 3 datasets, a holdout set of about 6,000 LDCTs, low-dose CT scans, from NLST participants, about 8,800 LDCTs from Massachusetts General Hospital, and about 12,000 LDCTs from Changgung Memorial Hospital, including people that used to smoke. Patients all over the world have validated it in over 85,000 low-dose CT scans.
Our idea is to develop a deep learning and CNN model that detects breast cancer in automated breast ultrasound images. We are going to run our automated breast ultrasound dataset through the Sybil model and then replace the original ResNet architecture with MobileNet and VGG16 architectures. We also plan to test the ENAS model and let it generate a CNN architecture by itself. Here's a visual of what we're going to do. So we start out with the original Sybil model, and what we will do is change the output to determine whether there is cancer present. We will run our ABUS dataset through Sybil and calculate our accuracy. Then we will replace ResNet with MobileNet and VGG16, and then we will test out the ENAS model and compare model accuracies. You can find the models and data here. So far, we have acquired over 34,000 ABUS images that altogether represent 100 patients. Using these images, we have converted them to DICOM files so that they can be packed into a JSON file with all their metadata. Currently, we are figuring out how to change the Sybil model to fit our data's components. We would also like to acknowledge ASDRP and Dr. McMahon for giving us the resources and opportunity to do this research. Any questions?